Chapter 2, Functions and their Graphs, Section 2.9, Inverse Functions. We'll begin looking at this topic with a simple example. Given two functions f of x equals x plus 4 and g of x equals x minus 4, compare their tables of solutions for selected values of x. So we'll begin by setting up a table of solutions for the function f. Notice f of x adds 4 to each x value, and here we've selected x equal to -1, 0, 1, and 2. So to compute the function value f of x, that is the y value, add 4 to each given x value. So -1 plus 4 is 3, 0 plus 4 is 4, 1 plus 4 is 5, 2 plus 4 is 6. Now we'll do the same with the function g. G of x equals x minus 4. So for each x that we've selected, 3, 4, 5, and 6, we'll subtract 4 to compute the function value g of x, again the y value corresponding to the given x. 3 minus 4, -1. 4 minus 4, 0. 5 minus 4, 1. 6 minus 4, 2. Now notice that the x's we chose for the second table are the y's from the first table. So if we first substitute into f and then take that result and substitute into g, g just takes us back to where we started from with f. For example, for f, x equals -1 is paired with 3. Then if we take the output for f and use it as the input for g, that is as the x value, that takes us back, g takes us back to -1. And this is something that happens for any x we would choose. If we substitute into f and then take the result of f and substitute into g, we're just back where we started. We see furthermore that we could say that the roles of x and y are interchanged. -1 corresponds to 3 with f. 3 corresponds to -1 for g. So the roles of x and y get reversed or interchanged. From these tables we may infer that if f of a equals b, then g of b equals a. In other words, g has the effect of undoing or reversing the action of f. So if a comma b is associated with f, then b comma a is associated with g. This effect can also be seen by performing the function compositions f composed with g and g composed with f. So let's do the composition f composed with g for a general x. F composed with g of x is defined as f of g of x, working from the inside out. G of x is x minus 4. Then f of x takes x minus 4 and adds 4 to it. That just brings us back to x. So we're doing what I described with the two tables, except we're showing that this happens for any x we might choose, not for any particular value of x. If we look at the function composition g composed with f, that is g of f of x. Here f of x is x, miscopied. F of x is x plus 4. We plug that into g. That would be x plus 4, g subtracts 4. X plus 4 minus 4 is x again. So here again we see that if we start at x, that's where we end up if we do a composition of g with f. So when this occurs, when we see this, what we might call a cancellation effect occur when we do the function composition of f with g or g with f, then we say that g is the inverse of f, and then we can use a new notation, a special notation used for inverse functions. We call g of x f inverse of x. Please understand, this is read as f inverse and not as f to the negative 1 power, which is what it probably looks like. The negative 1 here is not an exponent. It's merely a symbol to represent the inverse function. Now, the notation is connected to the notation we do use for inverse, as I'll explain in just a moment, so that you can see why we do use this, this notation. So we can say, instead of saying g of x equals x minus 4, we can say f inverse of x equals x minus 4 if f of x equals x plus 4. And then we can write the function compositions above as follows. F composed with f inverse of x, that is f of f inverse of x, equals x. And f inverse of f of x, or f inverse composed with f of x, or f inverse of f of x, is also equal to x. The results we've written above are often referred to as the cancellation laws of inverse functions. If the inverse of a function exists, it cancels that function under function composition in the same way that the reciprocal of a number cancels the number under multiplication. For example, For example, if I take 2 and I multiply it by its reciprocal, 1/2, we would say 2 and 1/2 cancel, leaving us with the number 1. In this situation, we can write 1/2 as 2 to the negative 1 power. And here the negative 1 is understood as an exponent, and 2 to the negative 1 represents the reciprocal of 2. With function composition, the f inverse notation is not referring to a reciprocal because the operation that we're using, the way of combining the functions, is not multiplication. If it were multiplication, we would use the reciprocal. But being function composition, it's not the reciprocal that gives us the inverse. It is a function rather that reverses the action of the original function. That is what actually represents the inverse. Furthermore, we may say that if g is the inverse of f, then f is also the inverse of g. That is, f and g are inverses of each other. So if two functions are inverses, we don't necessarily have to treat one as the function and one as the inverse. It's really just a matter of notation more than anything else. So if I have the function f and I know the function g is the inverse of f, I can write g equals f inverse. On the other hand, if I have a function g and I know that f is the inverse of g, I can say that f is equal to g inverse. It's just saying that f and g are inverses of each other. So we can call one function the invert, one function is the original and one function is the inverse. It doesn't really matter which one we call which. Usually we make a choice at the very beginning as to which one we treat as the original function, though. So finally, here's the definition of inverse function based on function composition. For a given function f, if a function g exists with the property that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f, then g is called the inverse of f, and we can rename g as f inverse. So notice here we're treating g as the inverse function, although again f and g are inverses of each other. So the inverse of a function is defined formally using function composition. Again, I will reiterate, the notation f inverse is not read f to the negative 1 power and does not refer to the reciprocal of f. So in other words, f inverse of x is not 1 over f of x. This is very commonly misunderstood by students. They just assume that because the notation looks like the notation used for reciprocal, that it represents a reciprocal. But it does not. So you have to be very careful of that. Let's now look at example 1 on the next page. Use composition to show that f of x equals 2x minus 4 and g of x equals x plus 4 over 2 are inverses. Now, we can actually sort of see that f and g are inverses just by looking at how the functions are defined. F of x takes an x, multiplies by 2, then subtracts 4. G of x, on the other hand, takes an x, adds 4, then divides by 2. So f first multiplies, then subtracts. G first adds, then divides. So again, the operation of g is in the reverse order of the operation of f. That would suggest that g is the inverse of f, f is the inverse of g. To verify this, however, we should perform function compositions. If we do the composition f composed with g of x, that is f of g of x, starting from the inside, this would be f of x plus 4 over 2. All right, then we're going to plug that into f. So whatever we plug into f, we multiply by 2 and then subtract 4. Now here the 2's are going to cancel. That gives us x plus 4 minus 4. We started with x, we end with x. F composed with g of x equals x. That is, f and g cancel each other. Let's also check g composed with f of x, performing the composition in the opposite order. That is g of f of x. Well, f of x is 2x minus 4. Whatever we plug into g, we add 4 to it and then divide by 2. Notice minus 4 and 4 cancel, so we end up with 2x over 2. Once again, we end up with x. So regardless of the order of the composition, f and g cancel each other. I would also just point out at this time that we said in the section 2.8 notes that generally if we reverse the order of function composition, we get a different result. When two functions are inverses, that does not occur. If we change the order of the composition, we get the same outcome either way. We'll continue with the notes in the next video.